Okay, so if I have a function y equal to f of x, which is a product or a quotient of a bunch of factors, and maybe some of these factors are being raised to powers, or they're going to have roots taken of them, or something like that, it's often easier to find the derivative of the natural log of f of x. So it turns out that we can use the logarithmic derivative and implicit differentiation to then find the derivative of f of x. So this is the process, and this is called logarithmic differentiation. We write log of y equal to log of f of x. Then we expand the right-hand side because it's a product and a quotient, and maybe there's some powers and things, and we can write it out nice and long and simply. Then we differentiate. What we get is y prime over y on the left by logarithmic derivative. And on the right, we have some function. What exactly is it? I don't know. It depends on the context. Then we solve for y prime by multiplying by y on both sides, and then we replace y with f of x to just get a function of x. Okay, so let's try this out. So let's use logarithmic differentiation on y equal to x to the 3/4 times the square root of x plus 1, all divided by 3x plus 2 to the 5th power. Now this is a product and a quotient, and each factor is something to a power. So first, I'm going to apply the natural logarithm to both sides. So we have log of y is equal to log of this thing, and I'm going to replace the square root with the 1/2 power. Then I am going to expand the right-hand side. So anything in the numerator becomes a positive term, anything in the denominator becomes negative. So I got log of 3/4 plus log of x to the 3/4 plus log of x squared plus 1 to the 1/2, because they're in the numerator, minus the denominator, log of 3x plus 2 to the 5th. Then I pull out the powers. And I get 3/4 log of x plus 1/2 log of x squared plus 1 minus 5 times log of 3x plus 2. I'm not going to pull out this 2 on x squared because it is not, the entire inside here is not a power now. It's x squared plus 1. The exponent is only on the x. Over here, I'm not going to pull out this 3 in front of the x because 3 is not a factor of the whole inside. It's only a factor of 3x. It's not a factor of 2. So this is good enough. Now the third step is I take the derivative. On the left-hand side, the derivative of log of y is y prime over y. That follows from just the logarithmic derivative. Over here, I have 3/4 times the derivative of log of x, which is just 1 over x, plus 1/2 times the derivative of log of x squared plus 1. So I take the derivative of x squared plus 1, which is 2x, and I divide that by x squared plus 1. Then I subtract 5 times the derivative of log of 3x plus 2. So I get the derivative of 3x plus 2, which is 3, over 3x plus 2. And then I'm going to sort of simplify them, get 3 over 4x plus x over x squared plus 1, because these 2's cancel, minus 15 over 3x plus 2. And I really only want to find y prime. So I'm going to multiply both sides by y, which gives me y prime by itself on the left. On the right, I have this expression times y. But I don't want to write y prime as a function of x and y if I already know y is a function of x. So I'm going to replace y with its original expression, and I'm not going to read out this entire expression, but this is our final answer. What we got from the logarithmic derivative times the original function. Okay. And I swear, this is a lot easier than applying the product rule, quotient rule, and the chain rule on this thing. Now there's really one final thing that we can do to functions that we haven't come up with a rule for yet. And this is exponentiation, namely taking a function f and raising it to the power of a function g. So we could have something called the exponent rule, I guess. This is different from the power rule because with the power rule, the exponent is constant. This is different from the derivative of an exponential function because for an exponential function, the base is constant. Here, both are variable. So you could memorize this if you really wanted to. The derivative of f to the g is gf to the g minus 1 times f prime plus the natural log of f times f to the g times g prime. I don't know about you, but I don't want to memorize this. I mean, this makes the quotient rule look like a walk in the park. So let's not do it this way. Yuck. Instead, if I write y is equal to f of x to the g of x, and I take the natural log, I get log of y is log of f to the g, and then the fact that logarithms play nice with exponentiation means that I could bring the g outside, and I get log of y is g times log of f. Then I can take the derivative and use logarithmic differentiation to figure out what y prime is. This, I swear, is a lot easier. So for example, let's take the derivative of f of x equal to x to the x power. A lot of people, when they see this, will just try to apply the power rule. They will bring the power x down, so they get x times x to the x, and then they reduce the power by 1, so that they get x times x to the x minus 1. It turns out when you simplify that, that's just equal to x to the x. That can't be right, because I've said the only function whose derivative is equal to itself is e to the x, or constant multiples thereof. So no, it can't be done just using the power rule. Instead, we'll use logarithmic differentiation. So I'm going to let y be x to the x, and then I'll take natural logs of both sides. Then I will expand the right-hand side, which in this case only involves bringing the power x outside and front like this. So I have log of y is x times log of x. Then I differentiate. The logarithmic derivative says the derivative of log of y is y prime over y. And then the product rule says the derivative of x is 1 times log of x plus x times the derivative of log of x, which is 1 over x. I simplify that to get log of x plus 1. So then I solve for y prime. Step 4. Multiply both sides by y to get y prime as log of x plus 1 quantity times y. And then I replace y with what it's equal to, which is x to the x. So my final answer for f prime is log of x plus 1 quantity times x to the x power. Let's do another one. I really like these kinds of problems for some reason. I don't know. Anyways, let's let y be sine of x to the square root of x power. Let's find y prime. Step 1. We'll take logs of both sides, and I'm going to rewrite the square root of x as x to the 1/2 because I'm going to have to take its derivative eventually, and so I might as well rewrite it as a power right now. Step 2, I can bring the power x to the 1/2 out in front like this. So I have log of y is x to the 1/2 times the natural log of sine of x. Step 3, I differentiate. The left-hand side is always going to be y prime over y. The right-hand side, I apply the product rule. The derivative of the first times the second gives me the derivative of x to the 1/2, that's 1/2 x to the minus 1/2, times the second guy, log of sine, plus the first guy times the derivative of the second. Now the second guy is going to involve the logarithmic derivative. It's log of sine of x, so its derivative is the derivative of sine over sine, so cosine over sine. So that means that y prime is equal to, once I pretty it up, I multiply both sides by y, I get y prime is log of sine over 2 root x, just bringing the 2 into the denominator and the x to the minus 1/2 into the denominator as root x, plus cosine over sine is the same thing as cotangent, and I'm multiplying that by root x. So that whole quantity times y, and then at the end of the day I have to replace y with what it is in terms of x. So I get log of sine of x over 2 root x plus cotangent of x times the square root of x, quantity times sine to the root x. So here is question 2. Evaluate the derivative of x squared plus 1 to the 1 over x. Use this logarithmic differentiation technique to evaluate.